Hello friends, today we will solve the GATE 2025 Electronics and Communication paper control system questions. Okay, so this is the first question. It is saying that the Nyquist plot of a system is given in the figure below. So this is the Nyquist plot. Okay, and let omega p, omega q, omega r and omega s be the positive frequencies at point p, q, r. So this is point p, this is q, this is r and this is s. Okay, so which of the following is true? So he is basically asking about gain crossover frequency and the point which represent phase crossover frequency. So gain crossover frequency is the frequency where this Nyquist plot or polar plot touches the unity circle. So this is point S. So omega s is the gain crossover frequency, and the point where Nyquist plot touches the negative real axis or minus 180-degree axis is the phase crossover frequency. Okay, so omega s is the gain crossover frequency and omega q is the phase crossover frequency. Okay, so this was the first question. Second question is on root locus plot. Is saying that consider a unity negative feedback system where k is greater than 0. The root locus of the system is shown below. For what value of k will the system in figure 1, so this is the system, closed loop system, will have pole at minus 1 plus j1. So it's a closed loop system, so it will have closed loop poles. So we need to find out where will it have, for what value of k will the system have pole at minus 1 plus j0. So this question does not require any calculation because in root locus, as we vary k in OLTF, we get the root locus plot. Okay, so for no positive value of k, the root locus plot, which is nothing but a locus of closed loop pole for different k values, is touching the pole at minus 1 plus j0. So these are basically closed loop poles only. Okay, this is going here, this is going here, then one is going here, and then another pole is going here, and then they are coming to zeros. So minus 1 plus j0, no pole will touch it. So for no positive value of k, we will get any pole here. Okay. So C is the correct answer. Third is a question on Routh-Hurwitz. Okay, so there is a polynomial 5th degree s ki power 5 plus 7 s4 plus 3s square minus 33s square plus 2s minus 40, and we need to find out the number of roots with negative real part, purely imaginary and positive real part. Okay. So we just need to make the route table. Okay, so this is like s ki power 5 is 132, s ki power 4 is 7 minus 33 40, then s raised to power 3 is basically this thing into this thing minus this thing, so it is 54 upon 7, and then 14 minus or minus 40 upon 7, so 54 upon 7, and then this is 0. So we can basically multiply the whole thing by by 7, 1 by 7, multiply by 7, so then this will be 54 54 0. Okay, you can multiply by 7 7, so this will be 54 54 0 s ki power 3, and then we have s square, which is again 54 into minus 33 minus 54 into 7 divided by 54, so this part is minus 40. Similarly this part is also minus 40, this is 0. Okay, so s raised to power 1 will be 0 0, because this is 54 54 0, this is 40, minus 40 minus 40 is 0, so this will be 0 0. So we are getting a row of z here. Okay, so row of z we are getting. Okay, so we need to make auxiliary equation. So from above row, so this will be minus 40 s square minus 40 equal to 0, which can be simplified as minus s square minus 1 equal to 0, and then we need to differentiate it with respect to x. So this will be minus 2s, and minus 2 will be now the coefficient. So here it will be minus 2 and 0 0, and then s ki power 0 will be, this is minus 40 0 minus 2 0, so this will be minus 40. Okay, because it is a minus 2, okay, into minus 2 into, wait a minute, minus 2 into minus 40, and then into 0 divided by minus 2, so this is minus 40. Okay, so basically we need to check, this is negative, this is negative, this is negative, but this part is positive. All about positive, all about negative, so only one sign change. So only one sign change means only one right half pole. Okay, and we know that purely imaginary root comes only due to auxiliary equation. Okay, so this is like a s square equal to minus 1, so s equal to plus minus a. So the roots on imaginary axis are 2, and roots on right half plane is 2, so left half plane is 2. So left is 2, right is 1, and imaginary part is 1. Another question was asked on compensator and controller. Okay, so here it is saying that let gs is equal to 1 upon 10 s square with the transfer function of the second order system. So this part is given as 1 upon 10 s square. A controller ms is connected to the system in the configuration. So this is a controller. Consider the following situation: there exists no control of the form ms is equal to ki by s, where ki is a positive real number such that closed loop system is stable. So this controller is in first case it is ki by s. Okay, and then we need to find out whether the closed loop system is stable or not. In second case, there exists at least one control of the form kp upon kp plus s kd, with kp and kd are positive, so that the closed loop system is stable. So controller is taking two form, ki by s integral controller, and this is like proportional plus derivative controller. Okay, PD controller. So in first, so it is basically Rauther-Hurwitz problem. So first we need to find out the closed loop transfer function. So in case 1, CLTF, which is a closed loop transfer function characteristic equation, GS HS equal to 0, HS is 1, and GS will be Ki, okay, Ki by S into 1 upon 10 s square. So this is Ki upon 10 s cube. So 1 plus Ki 10 s cube equal to 0. So which is like 10 s cube, and 10 s cube plus Ki equal to 0. So this part will be 0. So this is 10 s cube plus Ki equal to 0. So clearly it is a 100% unstable system, because s square and s ki power 1 terms are missing here. Okay, so no need to go for Rauther-Hurwitz, so it will always be unstable. Okay, so statement 1 is true, that there exists no control of the form like this, where so that the closed loop system is stable. So pure integral controller always pushes the closed loop system toward instability. This you already know, and this has been proved also here. This will make the system unstable. For second case, what we will do is, again we will make characteristic equation. One is gs hs equal to 0. So gs is kp plus khd into 1 upon 10 s square, so which is kp upon 10 s square plus kd upon 10 s, because 1 s and 1 s will cancel, equal to 0. So then it is 10 s square plus kp plus kds equal to 0. So this part will be 0. So this is 10 s square plus kds plus kp equal to 0. Now this part is positive, this part is positive, 10 is positive, and s ki power 1, s ki power square, s ki power 1, s ki power 0, all three terms are present. So yes, this closed loop system will always be stable, because in fact there can be multiple positive values of kd and kp, and this system will be stable. So first is true, and second statement is also true, that there exists at least one, in fact there are multiple controllers possible, so that the closed loop system is stable. Okay. This question was from Rauther's SFG. So here it is saying that consider the system in block diagram. Which of the following signal flow graph represents this system? So choose the correct. So one trick to solve this is that you can see here that in this main block diagram there are two forward path. One is this, another is this, but there is only one loop. Okay, there is no other loop. So two forward path, one loop. Okay, and whereas in case 1 there are two forward path, this, and again there are two loops. So this is one loop, okay, and this is another loop. So there are two loops, but in main actual block diagram there is one loop, so this part will be cancelled. Okay, option A cancelled. In option B you can see that there are two forward path, 1 and 2, and there is only one loop, so this can be an option. In case 3 also you can see that there is one forward path, there is second forward path, and again there are two loops. So there are two loops and two forward paths, so this part is cancelled, and also there is no negative feedback also. There is no -1 sign, so this part is again cancelled, this part is cancelled. In option D you can see that there is first forward path, okay, then there is second forward path, but then there is one loop and then there is another loop. So here also there are two loops, so again this part is cancelled. So basically only B will be answer. Why? Because you can see that you can find the signal flow graph of this thing by converting into SFG. Now you can convert the SFG in two ways. In first way you can take this summing point and takeoff point as different nodes, or you can combine them. You can combine both of them only when they are in alphabetical order. Okay, so here first is S and then there is T. Okay, so first there is S and then there is T, then you can combine them, but here first there is T and then takeoff point and then there is S summing point. So in this case you cannot combine them. Okay, so here I have kept them distinct, but here I have combined them. Okay, and this is basically exactly the second case. Okay, or and then I will get the transfer function as g1 plus g2 1 plus g1. Or what I can do is I can keep them different nodes, and even if I keep different nodes, then also I will get two forward path and one loop, and again the transfer function will be g1 plus g2 1 plus g1. Okay, so B is the correct answer. Or you can also find individual transfer function, like in this you get g1 plus g2 1 plus g1 plus g2 extra term, and here it is correct. Here also you are getting extra term minus g2, so this is correct term, this is also wrong. Okay, so you can find transfer function also, or you can directly see the number of loops. Here it has only one loop. Okay, so it was a good question. Last question is on, it is a tricky problem. It is on state space. It is saying that choose the system, consider the system where x1t, x2t, x3 are the three internal state variables and ut is the unit input signal. Okay, so it is the input signal, the normal form. Differential equation governing the system are given by this thing. So which of the following is true? The signal x1, x2 and x3t are bounded for all bounded input, and there exists a bounded input such that at least one of the signal is unbounded, and there exists a bounded input such that all the x1, x2, x3 are unbounded, and the signal x1, x2, 3 are unbounded for all bounded input. So one superficial way of handling it is that since it is a diagonal canonical form representation, so the eigenvalues will also be the closed loop poles. So eigenvalues are 2 minus 2 0, so closed loop poles are also 2 minus 2 0. So there is one right half pole. So one right half pole means what? Means the system is BIBU unstable. Okay, which means for a bounded input we will get a unbounded output, and that output, unbounded output, output of the system depends on state variable. Okay, so we can comment that at least one or more of the state variable is unbounded. So by that we can make B as the correct option. And signal x1, x2, x3 are bounded for all bounded input. This will be false because this right half pole will make it BIB unstable. Okay, so this part is wrong. And now how to handle C and D? That it is unbounded for all bounded input, and for a bounded input all are unbounded. So for that I think the best way is to make the differential equation. Okay, so like first of all you make differential equation x1 dot is equal to 2x1 plus ut. Okay, so x1 dot is equal to 2x1 plus ut. Okay, and let ut be a unit step. Okay, just an example. So let ut be unit step. Okay, so utical Laplace transform will be us, which is 1 by s. Okay, so when we convert it into differential equation, all three of them I have tried to convert them into first differential equation to Laplace form. Here also it is x2 dot is equal to minus 2x2t plus ut, and x3 dot is equal to only ut. Okay, I think it was this question. So here you can see that x3 dot is equal to only ut, because all three are 0, and x2 dot is equal to minus 2x2 plus ut. Okay. So then we take Laplace of this, so it will be s x1x minus x10 is equal to 2x1x plus us, and then it will be like x1s minus 2x1x is equal to x10 plus us, which is 1 by s. So x1s we take common, so this is s minus 2, and this is x10 s minus 2 plus s minus 2. Similarly here also I have done x2 s common, so it is s plus 2, and here it is x20 plus 1 by s. And similarly here also I have done x3s is equal to x30 plus 1 by s. Okay, now you can see that x1s is nothing but x10 upon s minus 2, and then after partial fraction it will be some a by s plus b s minus 2. So this part is basically giving us, when we take inverse Laplace, it will give us e की power 2t ut, so which is an unbounded. So for a bounded input ut, we are getting an unbounded x1t. Okay, whereas in second case what you will see that for a bounded input ut, you are getting s plus 2 terms, s plus 2, s plus 2 and s. So it will be a ut, it will be e की power minus 2t ut, and it will be b e की power minus 2 ut. So here for a bounded input we are getting a bounded x2t. Okay, similarly in third case, if we take ut as a unit step, then it will be x30 s plus 1 upon x square. So this is x30 ut plus t ut, which is ramp signal, so again unbounded. So in here for bounded input we are getting an unbounded x3t. Okay, so therefore this option makes sense, because there exists a bounded input such that at least one of the signal is unbounded. So for ut these two are unbounded, but this is bounded. Okay, and these incorrect because signal x1 x2 are unbounded for all bounded inputs. So we have seen that for bounded input we are getting a bounded x2t, and all three are unbounded is also done by this example. So correct answer will be B part. Okay, so these were all 6 questions. Thank you.